Okay, in section 2, we're going to look at the concept of domain and range of some different relations in math. Before we do that, though, we want to go ahead and review a concept called interval notation. Now, interval notation is a notation for representing an interval as a pair of numbers. So we're trying to basically express all the numbers that are between two values. So generally, those are done by putting the two numbers next to each other with a comma. So just a quick example could be 2 and 3. So those are all the numbers between 2 and 3. And if I put brackets around those, we would include 2 and 3. So it's all the decimals after 2, before 3, 2.1, 2.11, 2.2, all the way up to 3. If I put 2 and 3 both in parentheses, then that's all the numbers between 2 and 3, not including 2 and 3. So the example we have written here on the notes, parenthesis 3, comma 8, bracket 3, parenthesis, 8 with the parenthesis, is all the numbers between 3 and 8, including 3, but not including 8. So here are a couple examples where we could write interval notation, all real numbers. Now, all real numbers would be every number that we know in existence. Now, since we really don't have a smallest or biggest number, the way we write this is negative infinity to positive infinity. Infinities always get parentheses. This basically represents the smallest negative number and the biggest positive number and all the numbers in between. The next one we have is all real numbers less than or equal to negative 2. So if you think about a number line, here's negative 2. It's all the numbers that are less than negative 2 or equal to negative 2. So we want to also include this negative 2. So the smallest value, these numbers go smaller and smaller forever and ever and ever. So our interval notation, the smallest this is going to go is negative infinity, and the largest it's going to go is negative 2. Again, parentheses always for infinities, bracket for the number because we're including negative 2. So in general, these interval notations always are going to go smallest to largest. And we'll use interval notation a lot on a lot of things we talk about in this course. The last one, C, says all real numbers between 7 and 8 or larger or equal to 9. So we have basically two parts. We have between 7 and 8. So we have 7 and 8, and it doesn't say we include 7 or 8, just between those two, so those will both be in parentheses. And it also says larger or equal to 9. So that's going to be all numbers bigger than 9, so we'll include 9, and then all the way to infinity. Now when you have these two parts like that, we generally join those with a U. So this interval notation is how we're going to write our intervals of lots and lots and lots of numbers. So one place we're going to use this is when we talk about the concept of domain and range. Now this is a concept that hopefully you've seen before at some point, but domain is a set of values of the independent variable for where a function or relation is defined. Typically, this is the set of x values. So it's the values you plug in. The range is the set of values of the dependent variable for which the function or relation is defined. Typically, this is the set of y values. Now, the most important thing I want to point out here is where it's defined. Toward the end of this section, we'll talk about some functions that are not defined everywhere. There are some functions, if I give you a relation like y equals 2x, I can plug in any x value and there's no problem. I can get any y value, that's no problem. But that's not necessarily true of every mathematical relation. So there are two types of examples we want to look at. One is going to be the domain and range of finite sets, and one is going to be of an infinite set. So when you talk about a finite set, it's essentially a set that only has a certain number of elements. For example, our class is finite because there's only a fixed number of students in it. There's not infinitely many students in our class. So if a function has a set number of elements, then we call it finite. So here are two examples of finite relations. This first one is in kind of a set notation where it says set S is just these 3 points. So if I want to write this as kind of an XY table like you're familiar with, the first point is 3, 4, so 3 for X, 4 for Y. -1 for X, 4 for Y. And 10 for X and -5 for Y. So domain and range is very simple for this. And it's not a interval notation because it's a fixed number of elements. The domain are just the x values that this relation will take. The only x values that this function is defined for is 3, -1, and 10. So typically we'll just put those in brackets, 3, -1, and 10. Same idea for the range. The range is just going to be the y values. Now in this case we have a repeated y value. We generally don't write that twice. So we have 4 and -5 for our range. If you want to put them in ascending or descending order, that's fine. It doesn't really matter. The second example you see of a finite relation, this is what we sometimes call a mapping. So in a mapping, you see each of the arrow relating one set to the other. So this is essentially saying if I plug in 3 to this relation, I'm going to get a 2 out. So remember we said that the inputs that we typically get are also considered domains, and the outputs are considered the range. So in this case, set A is our inputs and set B is our outputs. So if I wanted to write what my domain is just all the things in set A. So that's 3, 4, 5, 6, and 7. Now my range is a little trickier because my range is going to be 2, 1, 9, and 12. Now you'll notice I did not include 3 and I did not include 8 because there's no arrow pointing to that, so that doesn't mean there's any value in the set B that a value in set A is related to. If it's not a relationship, then it's not in our domain and range. So if you have extra elements in something like this in a mapping, you would only include the ones that have the arrows. So now when we're looking at the domain and range of infinite sets are just like a finite set, so there are infinitely many points. So there's points among points among points among points. These are a lot of the times expressed as graphs. So if you think about a line from algebra, if I just do some linear equation, then all these points on this line are solutions to the equation, so they're part of the function or the relation. So there's all these points with x's and y's. So it's very difficult to actually list all those points out one by one because there's infinitely many of them. So a lot of times when we look for the domain and range of infinite sets, we'll use an interval notation like we talked about earlier. So if we look at this first example, it says find the domain and range of the function below. Express your answer in interval notation. So this graph, it has this kind of line that goes to the left here and an open circle. That means it's going up to this point, -2, -6, and it's essentially stopping there. It does not include that point. And then up here you can see the solid dot, where it's going to start there, and then it has this kind of turn, and it's going to keep going up. Now one thing you want to keep in mind, when you have this arrow, when it kind of goes off the paper, it's going up, but at the same time it's also going to the right. So when I talk about the domain, we're trying to talk about all the possible x values that this function can take. Well, if we think about the graph out on this section, the x values will get smaller and smaller and smaller and smaller. So the x values for the domain will go to -infinity. Now for the biggest value, it will also go off to infinity, because as this goes up, like we said, it's also going to the right. So these points that kind of keep going up here have increasing x values, and those x values will go up forever. So the really only question we have is, what about this point -2? Is -2 in the domain? And the answer is yes, because you have this solid dot. The solid dot, either place, is what makes it included in the domain. If they are both open circles, then you would not include it. So in this case, the domain is simply -infinity to infinity. Now the range is a little trickier. The range, we have two parts as well, because range we're talking about y values. Now if we talk about this bottom part down here, this kind of, again, this horizontal line going to the left, the y value on that is always -6. So when I start my range, I'm just going to include the element -6. And again, when you put in these kind of curly Q brackets, like we did for the finite sets, that means basically one thing. Now for this upper part, now we're talking about y values for the range, so we'll do our union. So the smallest y value it's going to take is down at this bottom point here, and that is going to be 0. It does include 0, so we'll put the bracket, and then the y values will increase as it goes up, so it'll be 0 to infinity. And then, of course, the parenthesis on infinity. So this one's a little different, where the bottom part only had one portion to it, just the -6, and then the upper portion's going everywhere from 0 to infinity. Let's look at another one that has some line parts to it. Now you'll notice in this one it has this line segment up there in the middle. These two, it doesn't really show it, but since it kind of goes off the page, we'll assume these are going to keep going down and to the right and down and to the left. So when I talk about the domain, I know it's going to start at -infinity, because if I think about this portion of the graph, it's going down, but it's also going left. And as it goes left, you get x values that are smaller and smaller and smaller and smaller. Now our first interesting question here is right here. And you see, and this is at -3, you see both of those are open circles. So since they're both open circles, I can't include -3. There's nowhere where -3 is defined. So we'll put -infinity to -3 with a parenthesis. So when we start again on this kind of line segment up here, we're going to start at -3 again, but we're going to stop now at 3 with a bracket because it is included. So now we have this part taken care of, where we have the -3 to 3, including that 3. So then we have a gap. So in this area, there's no graph. So there's thus no x values. So the next time we see a graph is over here at this closed circle, and we'll start back at 6, and then the x values go forever to infinity, because this thing is going down, but again, as it goes down, it's also going to the right. So on this graph, any point in these three intervals, if you pick a number, then you could have a point on the graph that has that x value. Let's talk about range. So if you talk about range, the lowest y value is obviously going to be -infinity, because you actually have two parts of the graph that are going down. Now this is a little tricky, because if you look here, this is where this part of the graph stops, at a y of 0, not including 0. But over here, this part of the graph goes all the way up to 1, including 1. And it doesn't have to be both parts, it's just either part, because it's any y value on the relation. So in this case, for the range, it goes -infinity to 1 with a bracket, because that's the y value that it stopped at. And then you have this little gap with the y value, because in this area, there's no y values, there's no graph for the y values. So the next place it starts is at that open circle, which is at a y value of 2. It is an open circle, so it's going to be a parenthesis. So parenthesis 2, and then the absolute highest point is going to be this closed dot up here at a y value of 4. So very important, remember, these domain are the x values of the relation, and these range are the y values. Very important to keep in mind. So now we've seen how to kind of find the graph, the domain and range of the graphs of some different functions and relations. But there are also some specific types of functions that we learned in our library of functions that have restricted domains, which means their domains are not everything. There are some x values that don't work. So that first one we're going to talk about is the square root function. The square root function's domain is always values that make it non-negative. So the square root must always be greater than or equal to 0. It can't be less than 0. It can be equal to 0, it can be greater than 0, but it cannot be equal to 0. And the reason is if I take a square root of a negative number, that doesn't give us a value. It gives us an imaginary value, but not a real valued solution. The reciprocal function, which is like a fraction function, is the domain is always values that do not make the denominator equal to 0. I can't divide by 0, so I cannot have any x value that makes it 0 on the bottom, because that's not allowed. The third and final one we'll talk about is the logarithmic function. The logarithmic function is always those values that make it positive. So in this case, it must be strictly greater than 0. Just like the square root, except it can't equal 0. So if we look at three functions, now one way to do this would be to graph them and see what they look like. But we want to kind of use this definition to kind of see if we can't find what the domain of these functions are. So the first one is the square root of x plus 3 minus 1. So really what we said is we want the square root to be positive. That means all the stuff inside the square root only has to be positive. So that means I need only the values inside, which are x plus 3. I need those to be greater than or equal to 0. And so now this is a very easy inequality to solve. We'll just subtract 3 from both sides. So x must be greater than or equal to negative 3. So in interval notation, the smallest value it would take would be negative 3 to infinity. And that is its domain. So that'll be true of all square root functions. You'll just simply try to find what makes the stuff under the root bigger than or equal to 0. Let's look at this function, g of x equals 3x over x squared minus 4. Now this is an example of a reciprocal function where you have a numerator and denominator. And remember the key here is we didn't want the bottom to equal 0. We can't have the bottom equal 0. So the question is, what numbers make x squared minus 4 equal to 0? And we don't want that to happen. There are lots of ways to solve this from algebra. The easiest way I'd say is just to factor it. This factors is the difference of two squares, x plus 2x minus 2, which both can't be equal to 0. And that, of course, is going to be x can't be negative 2, because in this factor, negative 2 plus 2 is 0. And for this one, the number that minus 2 is 0 is 2. So these are the two values it can't be, negative 2 and 2. It could be any other x. You can plug any other x in and be fine. So the way we'd write this is we'd say negative infinity to negative 2, because that's the first problem one. Parenthesis, union, and then all numbers between negative 2 and 2 are also good, because those are all fine. It's just these two that can't happen. Union 2 to infinity. And of course a lot of parentheses there because we're not going to include anything on those endpoints. So the last one we have is the logarithmic function, and it works very similar to the square root function. We're going to look and see what makes the inside of the log, but in this case, remember, it's strictly greater than 0. So we want to know what would make 2x plus 1 greater than 0. So if I solve this, subtracting 1 would give me 2x greater than negative 1. And then dividing by 2, we'd say x is greater than negative half. So any value greater than negative half would be defined for this log function, and any other value would not. Now again, notice there is no equal sign on a log. It is strictly greater. So we want all values bigger than negative half. So negative half is the smallest one for my interval notation. And again, I have the parenthesis because it's not equal. all the way to infinity. So that's kind of one example from each of the categories, the square root, the reciprocal, and the logarithmic. The last one I want to look at is one that kind of combines two. This one has a square root function and a reciprocal function. So the reciprocal function part is a little easier because you have a bottom of x minus 4. So if I'm thinking what would make x minus 4 not equal to 0, then x can't be 4 because I can just add 4 to both sides. So based on the denominator, we know that we cannot have an x of 4. But if we look at the top, we have a square root function, x plus 1 under the square root. And remember, for a square root function, we say x plus 1, the stuff under the root, has to be greater than or equal to 0. So if I solve this for x, we say x is greater than or equal to negative 1. So for this one, both these must be true. We must only use x's that are greater than or equal to negative 1, but we have to skip 4. 4 cannot be in the domain. So if I start to write this, well, of course, it'd be negative 1, which is the smallest value for this, and it normally would be to infinity, but we have to skip 4. So we go negative 1 to 4, parenthesis, because we're not including 4. But then once we get past 4, we're welcome to continue to infinity. So the square root is dictating that it has to be greater than negative 1, but the reciprocal part is saying we have to exclude 4. So that's a little bit on domain and range. So if you have questions, please let me know.